All right. This is catalysis. So a catalyst is just a compound that increases the rate of reaction without being consumed itself. So it lowers activation energy, the delta G of the transition state. It's important to note that it doesn't alter the thermodynamics, right? It doesn't change delta G. It doesn't change KQ. It doesn't change delta H. It only alters E sub A, the activation energy, and all the transition state values. Right. So there's three main ways a catalyst can speed up a reaction. The first thing is just by increasing the reactivity of the starting material. Um, like if we started with um, I don't know, an ester, like a carboxylic acid derivative ester, and we wanted to make it more reactive, we make it an acyl chloride, right? It's increasing the reactivity of a starting material. Stabilizing the transition state. So this could have to do with solvent effects or anything that makes it more likely for us to have the transition state form, right? Or we can change to a lower energy mechanism. So these three correspond with how we would see it on a free energy versus reaction progress diagram. And it's important to understand why um, we have those different things affecting the reaction progress versus free energy diagram in different ways. Um, okay, cool. So specific and general acid catalysis. Specific acid catalysis is when we have the proton donated before the rate determining step. So this involves strong acids. General acid catalysis is when we donate the proton during the rate determining step, right? So the main way that we can tell the difference between these is if we increase the amount of like buffer. Like how like if we're using a weak acid, we can increase the amount of buffer and the pH won't change. If it was a general acid catalysis, then we would just see an increase in the rate. But if it was specific, then we would not, right? So all it is the difference between H plus strong acids, hydronium ions, H3O plus, versus in general, like we just have to increase the amount of weak acid, right? So the pH doesn't have to change to make it faster. Okay, cool. So these are some examples of uncatalyzed, specific acid catalyzed, and general acid catalyzed, right? Uncatalyzed, we saw in the previous chapters that it was really slow. Specific acid catalysis, we make this center more electrophilic, which makes for a better attack, right? So this is characteristic of what we did in chapters 15 and 16 or 14 and 15, where we would either make a better electrophile or we would make a better nucleophile. In this case, we're making a better electrophile. General acid catalysis, this is just during the transition state. We have something for this to latch onto, kicked off this B. Cool. These are the free energy diagrams, right? And we can see the specific acid catalysis does appear to be the most effective in that it has the lowest energy humps. Also understand why it has two energy humps, right? Because it's sorry, there's two distinct steps. Okay, specific and general base catalysis. Specific base catalysis is when the proton is removed before the rate limiting step. So this involves strong bases. General is when it's removed during it. And it's the exact same types of concepts as what we just covered in acid-base catalysis for the acids. These are some examples of the transition states. And we can kind of get an idea of which ones are the best from these. But overall, we can just see that specific and general base catalysis have more favorable transition states, right? Okay, cool. Nucleophilic catalysis. Nucleophilic catalyst. We increase the rate of the reaction by adding a nucleophile to form a covalent bond with the reactant, right? So this is uncatalyzed, this is catalyzed, right? So this I is a better leaving group, right? So by making this switch, we're making it easier for the OH to attack. Cool. I is a better nucleophile than OH minus in polar protic solvents, since OH minus is held up by hydrogen bonds. It's a better leaving group than Cl minus. Cool. Okay, this is an example of catalysis. It's kind of similar to the reactivity of an acyl chloride. We're using something called DMAP, which also functions similarly to imidazole. The overall idea is that imidazole is this molecule. It's better nucleophile than H2O and a better leaving group than the ester. Cool. Okay, metal ion catalysis. So metal ions act in many ways very similar to Lewis acids to speed up a reaction. First of all, we can make an electrophile more electrophilic. We can make a leaving group into a weaker base, or we can make water a better nucleophile. These are the three ways that metal ion catalysis works. Okay. The first two are really, as you would expect. Even the third one is honestly, making a better nucleophile here, making a better electrophile here, making a better leaving group here. Cool. This is an example. We coordinate Zn to the O to make it this spot a better electrophile. The Zn is also coordinated to the OH to make this a better nucleophile. Um, with that, we have a slow step. We get to here. We remove the Zn. That allows these oxygens to come down. Um, sorry, not to come down. They just allows it to stay there. We coordinate to the thing that we want to remove. Then the electrons come down and they kick off this, right? Because this is a better leaving group now. Okay, so intramolecular catalysis really does make a difference, but the stereochemistry is very important here. So the groups that we want to do a catalytic attack with and the group that we want to leave have to be trans to each other because it requires a backset attack. So both groups need to be axial, not just trans, axial specifically. So this often comes in a chair structure. So we can see 70,000 to 1. Even though we have this sulfur group that you think like, oh, intramolecular catalysis, it doesn't work because they're on the same side. So this is kind of a ring structure drawn out. This is how it works. Ester hydrolysis and intramolecular catalysis, intramolecular general base catalysis. Again, just like you would expect. To make sure that we have the right orientation, you draw it out. This is slightly different in that it forms a ring and then it breaks the ring. But yeah, it's all the same general concepts. Cool. Okay. Biological catalysis, right? So all of the catalysis methods that we kind of talked about are, in isolation of the biological system. We talked about just the chemistry behind it, right? So in biological catalysis, obviously there's a lot more context to take into consideration. The first thing being the substrate will only bind the substrate at the active site. We're going from a substrate to a product. Lock and key model is an outdated model. This model was developed with the idea that an enzyme and a substrate would fit each other perfectly. This isn't exactly the case. We use something called an induced fit model, which is when the enzyme is slightly altered during substrate binding to produce a much stronger fit. So, how do enzymes catalyze reactions? So, the first thing they can do is hold reacting groups in proper orientation for a reaction to occur. The second thing, amino acid side chains act as acid, base, or nucleophilic catalysts. Many enzymes can also contain metal ion catalysts. Amino acid side chains can help stabilize the transition state through hydrogen bonding, electrostatic interactions, non-distortion forces. So at the end of the day, orientation for the first one, catalysis through acid-base nucleophiles for the second one, and for the third one, stabilizing transition state. Okay. Carboxypeptidase A. So now we're going to start talking about some of the enzymes that cleave peptides, right? So we have carboxypeptidase A, we have endopeptidases, and we might have one more. We have a lysozyme, right? So what is going on here? Like, what is the importance of these things? So carboxypeptidase A cleaves at the C-terminal end of a peptide chain. So a lot of problems that you're going to get in this course are going to be about trying to determine a sequence of peptides, given that you had a bunch of these enzymes and they cleave to different spots, and you'll be responsible for knowing like where these enzymes cleave and how to go about assembling the chain. So let's look at this, right? So this is an enzyme active site, and I don't think you're generally on the hook for memorizing these entire things. Just understanding the chemistry is generally sufficient, right? So we have tyrosine 248 here holding the C-terminal end. We have arginine 145, we have a hydrophobic pocket. We have this glues 270, which is acting as a general base catalyst. We have this zinc, this metal ion catalyst, which is lowering the pKa of H2O, making it a better nucleophile. We have arginine 127, which is hydrogen bonds. It stabilizes carbonyl O. We have the R group, right? So all the chemistry that we just talked about earlier, we can see how this active site is using it, and it's using it with specific context, right? It's these specific amino acids that are doing it. It's not just, functional groups, right? They're functional groups on particular things. Anyway, the point of carboxypeptidase A is to cleave at the C-terminal amino acid, and this can help you in trying to figure out and assemble, like, peptide chains. All right, acting as an acid catalyst, tetrahedral intermediate. Okay, you can kind of slow down and go through these, but it's the understanding of the chemistry is approximately what you would expect. Okay, endopeptidases. So there's three main endopeptidases. There's trypsin, chymotrypsin, and elastase. The specific points they cleave are all C-terminal, so they're all cleaving on the right side of an N to C-terminal amino acid chain. Um, Trypsin cleaves positively charged residues, so arginine and lysine. Chymotrypsin cleaves all the aromatics of phenylalanine, tyrosine, and tryptophan. And elastase cleaves glycine, alanine, serine, and valine, kind of the smaller amino acids, right? So these are examples of the pockets for each of them. And you'll see that we have for trypsin this aspartate 189, which we see has a negative charge on it. So we can kind of understand like, okay, like the pocket for the binding and the hydrolysis of these amino acids is negatively charged, which makes sense, right? Because the negative would hold a positive. For chymotrypsin, it's a little bit more complicated. The binding pocket is flat and nonpolar, which is very conducive to the 3D structure of aromatics with side chains. Um, and this one is very sterically hindered, right? You can see a lot of stuff in the way, which means that it only fits the smallest amino acids, these four. Cool. Reaction chemistry with chymotrypsin. Again, we cleave at the C-terminal spots. Okay, the catalytic triad. Okay, this is important, right? So the catalytic triad is something that you see in biochemistry and, 109C, and just in general, it's three different amino acids: aspartame, histidine, serine. Acidic, basic, nucleophile, right? So each of these three have roles that we've talked about. So let's look at this. This is the active site of an enzyme. We stabilize the developing positive charge in the imidazole ring with aspartate because it's acidic, right? Plus and minus. Histidine is basic, so it acts as a base catalysis or catalyst, sorry. So these electrons come down and they deprotonate this H here. And we have the nucleophilic catalyst here, this O, the serine that just got deprotonated and can now attack the carbonyl, kick up this O. General acid catalysis will stabilize the reaction because it stabilizes the transition state. We have something called the oxyanion hole, and basically negative on an oxygen, be more stable with hydrogens around it. Base catalysis comes down, grabs a proton, nucleophilic comes here, kicks up. New tetrahedral intermediate is formed, and then we detach from the polypeptides with this collapse. Okay. Site-specific mutagenesis. This is a technique where we substitute individual amino acids of enzymes, and that allows us to determine which amino acids are important for enzymatic activity and which aren't. So, I mean, this is pretty simple, right? Like you think that this enzyme does something, so you basically remove the enzyme and then see does it still happen, that thing that you think the enzyme did. And if it doesn't, then we know that that enzyme, or sorry, that amino acid was clearly involved. And if it does, then we are likely to assume that either there's a similarity between the amino acid that we put in place of the first one, or that that amino acid is not involved. Okay, lysozyme, peptidoglycan. So this is a lysozyme catalyzed hydrolysis, and it'll never occur right here. So one of the things in organic chemistry that we need to understand is that specific things occur in specific spots. So lysosome catalyzed hydrolysis will occur here in this beta position. So we have this to here. Okay, so beta stereochemistry is retained. It's an SN1 reaction or two SN2 reactions will occur. The OR group and NAM are responsible for binding selectivity. NAG is N-acetylglucosamine and acetylmuramic acid. If we look at these structures, there's a lot of NAM and NAGs involved. And this part isn't terribly specific, so I'm kind of not going to spend that much time on it, but it's kind of important to look at this. So this is the example of site-specific mutagenesis. This is glue 35 to aspartame, which reduces enzyme activity of a protein. Since side chain length and reach is reduced, any other substitution would lead it to be completely inactive. So this is an example of, switching out an amino acid to see like, oh, what's the actual difference? Yeah. Okay. If aspartame and glutamine have similar pKa's, why are they different or why are they in different states, acidic versus basic? So aspartame is surrounded by polar amino acids. The environment is similar to water. ASP is surrounded by non-polar amino acids. The environment is far different from water, right? So enzymes can also help to regulate local pKa's by varying side chains. After all, pKa's are just determined by their environment, by the pH, by the solvent, protic, aprotic, and the general medium that's used.